So this is kind of an important one. I don't think often enough, textbooks and so forth don't really use the phrase net work when they really should. So let's take a simple example. So if I push on this block from here to here, and we'll say I do it at constant velocity. We're going to ignore the part when I just start and when I stop. But in the middle, while I'm moving at constant velocity, I'm doing positive work. Based on what we talked about earlier, I think you would agree that my force is this way, the displacement's this way, I'm doing positive work. Now, while I'm doing positive work, friction is doing negative work. Is the amount of work that friction's doing negative, but the same magnitude, the same size as the amount of work I'm doing? Is there a way that we can argue that that is or isn't the case as I move this at constant velocity? Can we say that if I do 10 joules of positive work in doing that, can we say that friction does 10 joules of negative work? It turns out, in this case, yes. Here's why. So let's step back for a second and look at forces. If I'm moving this at constant velocity, what's true about all the forces on it? Take a second, pause the video, but you might want to, at this moment, draw a free body diagram for our block for the time while it's moving at constant velocity. Doesn't really matter what that velocity is, as long as it's constant. Draw your free body diagram yet? Let's see. So, what do we have acting on our block? Well, the block has weight and normal force. Now, as far as the discussion of work is concerned, could you explain to me right now, or to yourself, why it is that we do not consider normal force or weight to be players in the whole how much work was done conversation? That's right, because they are going to be perpendicular to the displacement in either direction. And forces that are perpendicular can't do work. They're perpendicular to the displacement. But the other two forces are me pushing it, so the applied force we'll say, and friction, kinetic friction, working against it. If the object is moving at constant velocity, or we're just considering that time when it's moving at constant velocity, then yes, all of these forces that we see here must all cancel out. Because we know, very early on in this course, we hopefully know that the phrase constant velocity is what we call dynamic equilibrium, and the object has an acceleration that's equal to 0, and therefore, remember, since net force is equal to ma, and if the acceleration is 0, that means it has a net force that is also 0. All those are true. As soon as I said we're considering the part at constant velocity. So, what can you say about my force and the force of kinetic friction? That's right. They got to be the same. While it's moving at constant velocity, everything's in equilibrium. My force this way is equal to friction's this way. But of course, my force is with the displacement, say both positive, and friction is against the displacement. Say friction's force is negative and the displacement's positive. You could look at it that way. Either way, friction is got a negative force, a negative amount of work that it's doing because it's opposite directions to the displacement. And I'm doing positive. So our forces are the same, and certainly I think you would agree with me that our displacements are the same. Right? We went from here to here. Friction and the block was the same block. It went from here to here. Displacement's the same for both. But in this case, there was work done by me, positive work. There's work done by friction, negative work. The two forces that are perpendicular, normal force and weight, they don't do any work because they're perpendicular. So in the end, what is the net work done on our block? as it moves on at constant velocity? And the answer to that is none. Here's another way to look at it. Net work can be looked at. So the net, come on now. Here we go, try again. There we go. The net work done on something, another way to look at that is it's the net force times the displacement. So there's work done by me in that case, and there's work done by friction, and you can calculate those works, but the fact is that there's no net work done on the block. So, because there's no net force. And if the net force is 0, there's got to be no net work. So it's important to note that there are plenty of situations where a problem might ask you about the work done by. So the work done by friction, the work done by the tension in the rope, the work done by the person pulling it, right? The work done by tension in the rope. Right? That individual work does not necessarily mean that that is the net work being done on the object. Now, if the problem is a frictionless surface, right? There's no friction here, and this is the only force, well then the tension is, then the work done by the tension is also, since it's the only force, it is the net force. I say only. These two, once again, don't matter. They cancel anyway. That force is also the net force and is also responsible for doing the net work on it. But if there's friction, well, let's see. If there's friction going against me, let's say I pull harder than friction does. What does the block do? Well, the block speeds up. Right? It doesn't maintain a constant velocity because there's a net force. And in that case, try that. And in that case, so now we're looking at the case where, hey, what if I pull on the block or push on it? Doesn't really matter. And my applied force, or tension, we'll use the tension from the one we just did. How about that? So I pulled on the string. We would call that, to be correct, we call that a tension force. Friction was less. Normal force and weight not only cancel each other out, but wouldn't matter anyway because the displacement would be that way. Although if they weren't there to cancel each other out, presumably it would be displaced, like when it falls off the table. So I should rephrase that. In this case, they cancel. They're not responsible for the net force. There is a net force, though, because this force is larger than this one. So the net force would be equal to the tension minus the force of kinetic friction. And you could find that net force if you had enough information, and you could use that to find the net work done on the object by taking the net force times the displacement. But another way to look at that is, could you figure out the work done by tension? So the work done by tension might be positive because the tension was in the same direction, right, as the displacement. And notice I'm not worrying about the cosine. I'm not pulling like this at an angle. We'll keep it simple. We'll pull parallel. Right. That tension is larger. So we could even make up a problem if we like. But the work by that tension would be its force, the tension, times the displacement. And that would be a large positive number. Meanwhile, the work done by friction would be the force of friction, which is a smaller force, correct? Right? Based on our diagram we discussed, it's a smaller force, times the same displacement. So this work would be smaller and negative, right? A smaller size, but a negative number. And this work would be positive and a larger number. So another way to look at the net work might be to just simply say the net work would be the combination, in this case, well, the combination of the work done by tension combined with the work done by friction. But of course, this will be negative, this will be positive, and this is the larger of them. So when you're done adding them, you will have an amount of work left over. Guess what? That's another way to find the net work. You could do it by finding the net force first and multiplying that times the displacement, or you could do it here. And in fact, if you take what I've written in this mess up here in the upper part, and let's look at that again. we'll clean this up a little bit. So if you recall, I have in the red over there, I had that the net work is equal to the work done by tension. I'll put the minus in there now. Minus the work done by friction, which is the minus comes from the fact that we know friction's work will be negative. And by the way, I think it was in black down here in the other part, I had the other way that we could have calculated net work and said, hey, if you know the net force and you multiply it times the displacement, you could get it that way. I would just like to point something out. This is why math is so darn useful. If you look over here, let's expound upon this. What's another way to look at the work by tension? Well, it would be the tension force times the displacement, like we mentioned. What about work by friction? Well, it would be the frictional force, kinetic in this case, times the displacement. You could factor that D out, couldn't you? Right there and there. You could factor that out. Reverse distribute it, I like to say. So if you pull that D out, you have T minus force of kinetic friction. In fact, I'm going to rewrite this. I'm going to say that T minus the force of kinetic friction times D. I'm just going to reverse the order. Instead of D times this, I'm going to put this times D. And the reason for that is because, wait a second. That thing right there. If I asked you to find the net force for that block, and you look at your free body diagram, what would you do? You would say, hey, the net force is equal to the tension minus the force of friction. You're experts at this. You had a whole marking period of it practically. Wait, that means that this is the net force, and really we're saying the same thing, just looking at it from two different perspectives. So you can figure out the work done, the two individual works, one positive, one negative, and then figure out the net work from that, or you can find the net force and multiply that times the displacement. But it's very important to note for an upcoming video in a little bit, 2 videos from now. Very important. I'm going to bring this up. Notice that the only way you're going to have a net work, a net amount of work done, is if there is a net force. Which means, think about this now, and we can bring up later, which means if there's a net force, that object's going to accelerate. Its velocity is not going to stay the same. And I'm not worried about situations where something turns, because that means the net force is perpendicular and there's no work done that way anyway. But, assuming the force is parallel, either with or against, there's going to be net work. There's going to be a net force. There's going to be a change in velocity. So keep that in mind for later. Before I leave, I want to just point out that the net force doesn't have to be positive. Right? If I take this and I slide it from here to here or so, whenever I let go, what's the free body diagram look like? So in that time when it was sliding to a stop, its free body diagram would have looked like this. Weight, normal, and it was, as it was sliding to this direction, the only force on it in the horizontal was kinetic friction. So that is the net force. And it's negative. Well, we can even call it positive, but the work done, it doesn't matter, because it's definitely opposite the displacement. When it was sliding, when it slides to a stop, friction's pushing this way, but it's moving this way while it stops. Right? Went from here to here. Displacement was that way. Friction was this way. Negative work. So in this case, there is a net work done, and the net is done by the net force, which is the force of kinetic friction. So in this case, the net force is the friction because there's nothing else to compete with it, times the displacement. But it's important to know that it's possible to have a net amount of work that is in fact negative. Net work does not mean there's some positive left over. It means it could be positive, it could be negative, it depends on the situation. But even in that case, right, this case, where it slides to us up, there's an acceleration. It's pointed that way, right? The direction of the net force. So, once again, the object's velocity changed. It got smaller. Right? So if my force is bigger, the speed gets bigger. But in this case, for example, it's small. So, net work can be positive or negative. Keep that in mind, because when we start talking about kinetic energy, which is related to velocity, there's a very important physical law that we discuss, and it's really helpful for solving problems.